on Friday by 2 p.m. So if you still need help with that, definitely make sure you meet with me during office hours. If you are struggling with certain sections of that prereq assignment, then we probably also need to have a discussion of how ready you might be for calculus, because I don't want us to get too deep into the semester and you realize that you're completely over your head. So no shame if you want to meet with me and talk about how ready you are for this class. So for today's notes, we are going to be looking at limits graphically. I do have the chat open, so if you want to type in questions into the chat, you're more than welcome to. But there's only 21 of you in this class. So if you also just like unmute your mic and ask the question, that seems to work best. And that's also true in case I start moving too fast, because I can't really see how much you've written down. And I tend to talk fast. So if I'm going too fast, just like unmute your mic and yell at me and I'll slow down. But this is being recorded in case you want to watch it later for fun or whatever. But if you want to tell your notes something today, it's going to be an introduction to limits, and we're going to be looking at limits graphically. And we're going to spend today and tomorrow looking at limits graphically. So there's not going to be a lot of numbers today. There is going to be just a lot of visual stuff happening today. Calculus is based off of 3 main topics. We have what's called limits, and then limits allow us to talk about derivatives and integrals. So limits is kind of easing into this calculus content. So before I give you a definition, I think the notation is important because we will see it so often. So this is the notation that we're going to be using for limits. So we use LIM to abbreviate a limit. Underneath it, written kind of in small letters, we'll have X. It could be a different variable, an arrow, and then a number. That number could also be like a plus or minus infinity. We have the function after it, and then in this case, I have equal to 3. So how I change all that math symbol into a sentence is when I see that statement, I read this out loud as the limit as x approaches 4 of f of x is 3. And the main word I want to focus on here is this word approaches. It's kind of what this arrow is representing in the symbol. And that's really what a limit is talking about. A limit is going to refer to what the function is doing as you get infinitely close to a certain x value. So I have 2 just blank graphs up here. I'm going to draw 2 graphs that would have a limit as x approaches 4 being equal to 3. One example of a function I can draw, and I'm just going to make something up kind of random. We'll do like a pseudo parabola. This is a graph where the limit as x approaches 4 is equal to 3. How I can tell that? So x equals to 4 is right here on my graph. And when I look at a limit, we want to talk about what the graph is approaching from the left and the right-hand side. So as I approach x from the left, and as I approach x from the right, we look at the y value that that function is approaching. Well, what y value is this function approaching? It is approaching the y value of 3. And then you might ask yourself, well, duh, Mr. Brown, f of 4 is 3, so is a limit just where the function is at? And that's not always true. For example, I can draw another function. Let's just do a line this time. But I'm going to put a hole on it. This function also has a limit as x approaches 4 being equal to 3. So again, I have 4 on my graph right here. Here's the 3. And so we can say the limit as x approaches 4. So when you're looking on both sides, as x gets closer and closer to 4, the y values get closer and closer and closer to 3. Remember, a hole on a graph means that the function does not exist there, but it does get like infinitely close to that open circle. So both of these graphs have a limit as x approaches 4, and they both equal to 3. For one, the function existed there. For the other, the function did not exist there, but we're talking about what it's doing as it approaches that value. Questions so far?
No.
All right. So lots of definitions today. The next part I want to look at is as we are going towards an infinity. So limits can also approach an infinity. So I have the limit as x approaches positive infinity and the limit as x approaches negative infinity. And I just chose an exponential graph to talk about it. It could be really any graph. And limits at infinity are going to be directly related to end behavior. In fact, if you remember from a previous math class, if you wrote the end behavior like as x approaches infinity, f of x approaches positive infinity, you are really doing a limit. Like end behavior is a limit. You just didn't call it that in your other math classes. I also think of limits at infinity as being associated with horizontal asymptotes. So when we see what is the limit doing as x approaches a positive negative infinity, we want to look at the far extremes of the graph. So positive infinity is on this side, negative infinity is of course on the left-hand side. And you want to see what the value is doing as those x values go further out. Again, remember the limit does not say the graph is located there, it just says it is approaching there. And the answer to a limit is always a y value. So let's do as x goes to positive infinity first. Looking at this graph, someone who feels brave, what do you think the limit as x approaches positive infinity of this graph is going to be?
-2.
-2, correct. I think that was Laurel. -2. So we have an asymptote here. So if you see an asymptote, it doesn't hit the asymptote. It will never be -2, but it is approaching -2. Someone else, what do you think the limit is going to be as x approaches negative infinity? So as x goes backwards towards negative infinity, where's the graph going?
Is it infinity or positive?
It is infinity. It is positive infinity. I'm not going to put equals positive infinity because infinity is an idea, not a number. Since it's increasing without bound, we can also say that the limit, and if you see Mean Girls, this is probably your favorite line, are one of them. But we can also say the limit does not exist. So when a graph approaches positive or negative infinity, since infinity is not really a number, like you can't ever reach infinity because infinity is by nature infinity, we are going to say D and E or does not exist. Some people like to be super fancy and say it does not exist because it approaches infinity. But either of those answers are okay. Both of them would be counted correct on both my assessments and on the AP exam. So we have limits approaching a number. We have limits approaching infinity. We also have one-sided limits. And so with our one-sided limits, we have these little positive and negative signs in your, kind of like in the exponent. In a one-sided limit, you only have to look at it from one side. So how I interpret this, when you see a minus in the exponent, that means you are going to just approach 1 from the left. And the way I think about that, if you think about a number line, the negatives are on the left-hand side. When I see as x approaches 1 with a plus sign, that means you are going to approach from the right. And if you see nothing there, so this is what we talked about in that first slide, you always have to approach from both sides. So we have left-hand limits, right-hand limits, and two-sided or both sides limit. So then we can go ahead and think about this one. If I want to talk about the limit as x goes to 1 from the left, it means we're going to look at where 1 is at, and we're going to approach 1 from the left-hand side. What's going to be our answer as x approaches 1 from the left-hand side? If anyone wants to take a stab at it.
2.
2. Does it matter if there's an open circle? No. It's still approaching 2, so that's what the limit is equal to. Someone else, what are we going to say the limit is equal to as we approach 1 from the right-hand side?
-1.
-1. So coming in from the right-hand side, it's closed, but it still exists, and it's -1. What do you think we're going to say the answer is when we approach just x approaches 1 without the plus or the minus there?
2 common -1.
So it is approaching two different things. When we talk about a limit, we're not going to say it can't really approach two different things at the same time. So when we see just x approaches 1, we're going to say d and e. Why are we going to say d and e? Because what's happening on the left-hand side does not match what's happening on the right-hand side. So for a limit that you're considering both sides for, the left and the right both have to match up. And that actually leads us to our first kind of definition that I want us to use and our first concept. Anyone still copying anything on that slide before I change it? All right. And that's going to be with a two-sided limit. So a limit, and I kind of put parentheses in here, if we don't see a plus or minus, we always assume it's a two-sided limit. So we have a limit exists if and only if the limit as x approaches c from the left of f of x is equal to the limit as x approaches c from the right of f of x. We will look at a lot of kind of math theory in this class. So like when you see a statement like this, you should be able to interpret what that means. So when we see this statement, we know basically that the limit on the left is equal to the limit on the right. If the left and the right hand side limits are equal to each other, then the limit overall does exist. And so we can write it as the limit as just x goes to c of f of x exists. So I said a lot of these notes are going to be visual, so I'm just going to kind of show you examples of graphs of like, hey, when you see a graph that looks like this is what it means. When you see a graph that looks like that, this is what it means. So some common does not exist situations, like we're just going to be talking about what's happening at some random x value c for all of these. Most common case when you have a limit not existing is when you have a piecewise function. Whether open or closed holes, it doesn't matter. So the left and the right hand side don't match up. To be clear, the limit only doesn't exist from both sides at c. Like if I choose any other x value, like if I just pick what I'm about to do in red, if I choose a point there, the limit does exist because the left and the right hand side matches. So just at c is what we're talking about in this case. You can also have an example, very obvious one, like a vertical asymptote. Clearly the left and the right hand sides don't match up. Or you can have one where like one side's an asymptote and the other side is like a piecewise. In all three of those cases, the left-hand side and the right-hand side don't match up. So we would say that the limit is not going to exist at C in those locations. Questions or concerns?
Yeah, so the limit is always y, right?
The value of a limit is a y value, yes.
Okay.
Or dependent variable, if you want to say it that way. And then kind of the last concept thing I want to talk about is the difference between values and the limit. So I added this after teaching calculus a few years. I did realize I need to make this distinction. Up until this point, when you're talking about like functions, you often talked about the value of the function. So like when I say f of 2, that's an example where you're asking about the actual value of the function. Like is asking where is the function at that location. Whereas the limit, when you're comparing it, it is asking for the limit, which when we say limit in math, is not asking you where the function is at, it is asking what the function is approaching. Sometimes those are the same thing, and sometimes those are not the same thing. For example, looking at this problem, what would you say? I have a piecewise function. What would you say the value of f of 2 is? Where is the function when x is equal to 2?
3.
3. So we have a solid circle here. That's where the function is at when it's 2. But what will be the limit as x approaches 2? So what is it approaching as you come in from the left and the right-hand side?
1.
1.
1. So we have a compare and contrast of like what is the value and what is the limit. So for at 2, the value does not equal the limit. Could someone give me an x value where the value would equal the limit? And don't think too hard.
Like in a quadratic, like at the vertex?
No, just give me an x value number. Try that. Look at an x value and just pick one, and we'll talk about it. So let's talk about, we'll say -1. At -1, would the value be equal to the limit as x approaches -1?
Yeah.
Yes, they would be. So f of -1 is, I don't know, we'll say about 2. The limit as x approaches -1 is also that same value. So pretty much everywhere but 2, the value is equal to the limit. So that's kind of the first distinction I want to make is what's the value, what's the limit. Some students like to just kind of simplify it, and is if your function is continuous, then the value and the limit will always be the same thing. So I'll say it again. For a continuous function, the value and the limit at a particular x value will be the same. You really only have issues with the value and limit not being equal to each other if you have holes in the graph or if you have like a piecewise function. Any questions so far?
Yeah. Could you do an example where the value is not equal to the limit?
That would be what I have up here as x goes to 2. So the value was at 3. So this is the value up here. The whole is what the limit is approaching when x is going to 2.
Is that the y value?
Yes. So this is, when I say at 2, I'm talking about at x is equal to 2. Because in this case, the limit is the y value of 1. The value is the y value of 3. I have some more like this. Bear with me. I promise. So these next kind of slides, I don't have really numbers on them. I just want to kind of talk about them in general. Some of them I won't even write anything on the screen for you. So we know that when we have a graph, we could have closed holes and open holes. When we talk about these, we can talk about things like the value of the function, and I can talk about the limit of the function. And I'm just going to choose a generic x value of c here. For the closed circle graph, the one that I have in red, does the value exist at c? Yes, we can see it's a closed circle, so the value does exist. That's f of c. Does the limit exist? Yes, looking from the left and the right, the limit does exist. The one in green is just an open circle. There's no points defined anywhere else. So this one has no value at c, but the limit as x of c does exist because you are approaching something from the left and the right. So that green one would be another case where the value is not equal to the limit because in fact the value doesn't even exist. It's undefined because there's just an open circle there, but the limit itself would exist because the left-hand side matches with the right-hand side. Other shapes you kind of see in graphs would be something like this. That's the same one we did. Let me get to the right slide. Yeah, try this one for me. So in your notes, this is just a random graph I made. We don't really have any numbers here. We have this x value of c, and I want to talk about the limit from the left, the right, the limit overall, and the value. And all I want you to determine, since there's no numbers, you can't find them exactly, but I just want you to think to yourself whether it exists or whether it doesn't exist based off of what you see. So take a moment just to think, does it exist or not? So the limit as x approaches c from the left, would that exist, yes or no?
Yes.
Yes, so it's coming in from the left-hand side. So it does exist. The limit as x approaches c from the right-hand side, would it exist?
Yes.
Yeah.
Yes. Would the limit overall exist?
Yes.
Yes.
Yes. If you were asked to explain how you know the limit overall exists, what would you say?
They're both approaching the same number.
They're both. The limit from the left and the limit from the right is approaching the same number. What would you say about the value of that function? Would it exist or not exist?
No.
Is there a portion of the function that exists at c?
Yes.
Yes, so it's floating above it, but the value does exist. So f of c does exist. But this is the case where the value, which is that closed circle hanging above the function, does not equal the limit. Because the limit is the open circle in this graph, the value is the closed circle.
So if the value had a different x value, then it would not exist.
Well, all of these we're talking just about this made-up value of c. So we're only considering that same c value for all of them right now.
Okay.
So go ahead, try these. Again, you can write it down in your notes, just kind of get it in your head. I have a green graph that's a piecewise with a jump and 2 open circles. And then I have a piecewise in purple with an open and a closed circle. And I just want you to think to yourself, does it exist from the left? Does it exist from the right? Does it exist overall? And does the value of the function exist? And then you can kind of expand that and think, well, is the value equal to the limit? But go ahead and determine whether each of those 8 things exist or don't exist for the 2 graphs. And I'll give you a moment to try that out first. And this is the last slide we'll do today. We'll finish up the rest of the notes tomorrow. It'll probably take less than 10 minutes, so you have more time to work on homework tomorrow.
Is there any homework tonight?
I will assign it, but I'm not checking. The only thing that's due is that prereq, which is due on Friday. Your first set of homework, I'm not checking until the day of your quiz, which is not until next Friday. So you have some time. So looking at this green graph, does the limit as x goes to c from the left exist?
Yes.
Yes.
Yep, it exists. What about the limit as x goes to c from the right?
Yes.
Yep.
Yeah.
What about the limit overall?
No.
No.
Nope, the left and the right do both exist, but they do not match, so it does not exist. What about f of c? Does the value of the function exist at c?
No.
No, you have no value existing. There's 2 holes, so you don't have a value there. If you can't have a value, then you also don't have, they can't be equal. Let's look at the purple one. Does a limit exist from the left?
Yes.
Yes.
Yep. From the right?
Yes.
Yep. Overall?
Oh.
No.
No. Does the value exist though?
Yes.
Yes.
Yes, there is a value, and the value would be whatever y value is at that closed circle. So that's where I'm going to go ahead and stop today's notes. Like I have 2 more slides to do, but they're a little bit more crazy with the asymptotes, so I'm going to hold off on doing them today. Here's a checklist of things that I want you to make sure you can get done today, and then I'll kind of wrap up class. There's still a few of you who haven't joined my Remind, so do that so you can reach out to me in case you have any questions. If you haven't signed up for the section in my AP classroom, please go ahead and do that today. You can find the code if you click on the assignment and then look in the description of that first assignment. Continue working on homework number 0. Those are prereqs which are due on Friday. Again, if you have concerns that you're not ready for this class because the prereq is challenging to you, then we definitely need to have that discussion. And then if you want to get started on homework 1, you can. It's not due until the 26th, so over a week away. But homework 1 is actually probably pretty easy, especially the first page, because you basically look at the graph and find out what the limit is. Tomorrow we'll finish these notes, and I have like a little in-class practice that we can do. But other than that, I am going to stop the recording, and class is kind of over. I got really nothing else to say. So if you're a good